Welcome to this rigorous scientific investigation of the photoelectric effect. Today we will follow the experimental workflow that revealed a profound threshold behavior that classical wave theory simply could not explain. In the late 1800s, physicists believed they understood light completely. Maxwell's electromagnetic wave theory had unified electricity, magnetism, and optics. Light was a wave, period. But some experiments were about to shake this confidence. Let's begin with the actual experimental apparatus. We have a metal surface in a vacuum chamber. When light hits this surface, we can measure if electrons are emitted. Here's our setup. Light strikes a metal surface. If electrons are emitted, they create a photocurrent that we measure with an ammeter. Simple enough. Our first task is systematic measurement. We vary the frequency of incident light and measure whether electrons are emitted. Let's keep intensity constant for now. Classical wave theory makes a clear prediction. Since waves carry energy proportional to their intensity, any frequency should eventually emit electrons if we wait long enough or increase intensity. But that's not what happens. Below a certain threshold frequency, no electrons are emitted, period, no matter how intense the light or how long we wait. Here's the data. Below threshold frequency, nu-zero, absolutely zero current. Above threshold, current increases with frequency. This sharp threshold is completely inconsistent with wave theory. Let's be quantitative. For sodium metal, the threshold frequency is about 5 times 10 to the 14th hertz. That's in the visible to ultraviolet range. Nu-zero approximately equals 5 times 10 to the 14th hertz for sodium. Using C equals lambda nu, this corresponds to a wavelength of about 600 nanometers, which is orange-red light. Lambda 0 equals C over nu-zero, approximately 600 nanometers. Step 2 in our workflow. Let's investigate intensity. Classical wave theory says more intensity means more energy delivered, so more energetic electrons should be emitted. We fix the light frequency above threshold and vary only the intensity. We measure both the photocurrent and the maximum kinetic energy of emitted electrons. Here's the second shock. Increasing intensity increases the number of electrons emitted, but does not change their maximum kinetic energy at all. Left graph. Current increases linearly with intensity. Right graph. Maximum kinetic energy stays constant regardless of intensity. This is absolutely baffling from a wave perspective. Think about it. If light is a wave washing over the metal surface, more intense light means more energy per second. Electrons should absorb this energy and come out faster. But they don't. Good science demands reproducibility. Let's test multiple materials. Each metal should have its own characteristic threshold frequency. Different metals, different thresholds. Sodium at 600 nanometers, zinc at 350, gold at 260, copper at 280. Each metal has a precise, reproducible threshold. This is a fundamental material property. The minimum energy needed to liberate an electron from a particular metal is called the work function, denoted phi. It varies by material. Now we're at the heart of scientific method. We have data that contradicts classical theory. Time to propose competing hypotheses to explain threshold behavior. Hypothesis 1. Maybe electrons need time to accumulate enough energy from the wave. Perhaps low-frequency light just takes too long. Hypothesis 2. Einstein's radical proposal from 1905. Light comes in discrete packets called photons, each with energy h nu. No packet, no electron emission. Let's test hypothesis 1 quantitatively. Suppose we use very dim light, say 1 microwatt per square meter, hitting a target area of 1 square nanometer. Intensity equals 10 to the minus 6 watts per square meter. Area equals 10 to the minus 18 square meters. The power delivered to this area is intensity times area. Power equals 10 to the minus 24 watts. That's incredibly tiny. The work function of sodium is about 2 electron volts. In joules, that's 2 times 1.6 times 10 to the minus 19. Phi equals 3.2 times 10 to the minus 19 joules. Time equals energy over power. Time equals 3.2 times 10 to the 5th seconds. That's about 3.7 days. But experimentally, when we turn on light above threshold, electrons are emitted instantly. No delay, not even microseconds. This demolishes hypothesis 1. Step 5. Design an experiment that definitively separates frequency effects from intensity effects. This is the stopping potential experiment. We apply a reverse voltage to stop the most energetic electrons. The stopping potential V sub S tells us the maximum kinetic energy of electrons. We make the collecting electrode negative. Electrons must overcome this repulsive potential. At stopping potential, even the fastest electrons can't reach the collector, so current drops to 0. At stopping potential, the kinetic energy of the electron equals the potential energy it must overcome. Kmax equals EVS, where E is electron charge. Now we systematically vary frequency and measure the stopping potential for each frequency. Keep intensity constant. Remarkable! We get a perfectly linear relationship. Stopping potential increases linearly with frequency. The x-intercept is the threshold frequency, and the slope is universal. Here's the crucial point. The slope of this line is the same for all materials. Only the x-intercept, the threshold frequency, changes with material. Einstein proposed a radical equation that explains everything. Each photon has energy h nu. Energy of photon equals h nu, where h is Planck's constant. When a photon hits an electron, energy is conserved. The photon energy goes into liberating the electron, which requires work function phi, plus the electron's kinetic energy. H nu equals phi plus Kmax. Rearranging gives us Kmax equals h nu minus phi. Kmax equals h nu minus phi. Since Kmax equals EVS, we can substitute. EVS equals h nu minus phi. Divide both sides by E. Vs equals h over E times nu minus phi over E. This is the equation of a straight line. Vs is y, nu is x, slope is h over E, and intercept is negative phi over E. Final validation step. The slope h over E should be universal. Let's calculate what it should be and compare to experiment. Planck's constant h equals 6.63 times 10 to the minus 34 joule seconds. H equals 6.63 times 10 to the minus 34 joule seconds. Electron charge E equals 1.60 times 10 to the minus 19 coulombs. E equals 1.60 times 10 to the minus 19 coulombs. The slope is h divided by E. H over E equals 4.14 times 10 to the minus 15 volt seconds. Experiments measure the slope with exquisite precision, and it matches 4.14 times 10 to the minus 15 volt seconds exactly. This confirms the quantum hypothesis. Let's make a quantitative prediction. Suppose we illuminate cesium metal with light of wavelength 400 nanometers. The work function of cesium is 1.95 electron volts. What stopping potential do we predict? First, convert wavelength to frequency using C equals lambda nu. Nu equals C over lambda equals 3 times 10 to the 8th divided by 400 times 10 to the minus 9 equals 7.5 times 10 to the 14th hertz. Calculate photon energy using E equals h nu. E equals h nu equals 4.97 times 10 to the minus 19 joules. Let's convert to electron volts. Divide by E. E equals 3.11 electron volts. Now use Kmax equals E photon minus phi. Kmax equals 3.11 minus 1.95 equals 1.16 electron volts. Since Kmax equals EVS, and we're already in electron volts, Vs equals 1.16 volts. Vs equals 1.16 volts. This is our prediction. We could perform this experiment and measure the stopping potential. If we get 1.16 volts, Einstein's theory is validated for this specific case. Students often ask, if one photon ejects one electron, why does increasing intensity increase current? Increasing intensity means more photons per second hit the surface. Each photon above threshold can eject an electron. So more photons equals more electrons per second, which means more current. Crucially, each photon-electron interaction is independent. The energy of individual photons doesn't change with intensity, only their number changes. Here's a visualization. Low intensity, few photons. High intensity, many photons. But each photon has the same energy h nu, determined only by frequency. The photoelectric effect had revolutionary implications for physics. It provided the first direct evidence that light has particle properties. This introduced wave-particle duality. Light exhibits both wave properties, like interference and diffraction, and particle properties, like the discrete energy packets we see in photoelectric effect. The photoelectric effect was crucial in the birth of quantum mechanics. Einstein received the Nobel Prize in 1921 specifically for his explanation of the photoelectric effect, not for relativity. The photoelectric effect isn't just historical curiosity. It has crucial modern applications. Solar cells rely on the photoelectric effect. Photons excite electrons in semiconductors, creating electrical current. Understanding threshold energy is crucial for solar cell design. Photodetectors in night vision equipment, digital cameras, and countless sensors all exploit the photoelectric effect. Photoelectron spectroscopy uses the photoelectric effect to probe the electronic structure of atoms and molecules. Let's review the rigorous workflow we followed. This is how science actually progresses. Step 1. Systematic measurement. We measured electron emission versus light frequency and discovered sharp threshold behavior. Step 2. Controlled experiments. We systematically separated frequency effects from intensity effects. Step 3. Reproducibility. We verified the threshold exists for all metals, though the specific value varies. Step 4. Competing hypotheses. We formulated testable alternatives and showed classical accumulation time fails. Step 5. Critical experiment. The stopping potential experiment provided quantitative validation of Einstein's equation. Step 6. Quantitative prediction. We calculated the universal slope, h over E, and found perfect agreement with experiment. Let me emphasize the key conceptual points you must understand. The threshold frequency is absolute. Below threshold, zero emission regardless of intensity or time. This is incompatible with wave theory. Photon energy depends only on frequency through E equals h and u. Intensity affects number of photons, not individual photon energy. Emission is instantaneous above threshold. No accumulation time. This directly contradicts classical predictions. The slope h over E is universal, the same for all materials. Only the work function phi varies by material. Let me leave you with a challenge calculation. Ultraviolet light of wavelength 200 nanometers strikes a metal surface with work function 4.5 electron volts. Calculate the maximum kinetic energy of emitted electrons. First, calculate photon energy. Frequency equals c over lambda equals 3 times 10 to the 8th over 200 times 10 to the minus 9 equals 1.5 times 10 to the 15 hertz. E equals h nu equals 9.95 times 10 to the minus 19 joules. Convert to electron volts. 9.95 times 10 to the minus 19 divided by 1.6 times 10 to the minus 19 equals 6.22 electron volts. E equals 6.22 electron volts. K max equals E photon minus work function equals 6.22 minus 4.5 equals 1.72 electron volts. K max equals 1.72 electron volts. That's the answer. The photoelectric effect represents a watershed moment in physics. It forced us to abandon purely classical thinking. It revealed that nature is fundamentally quantum at small scales. Energy is quantized, coming in discrete packets. It showed that our intuitions from everyday macroscopic experience can completely fail at atomic scales. Most importantly, it demonstrated how rigorous, systematic experimentation guides theory development. Data forces us to revise even our most cherished assumptions. This experimental workflow, systematic measurement, controlled experiments, competing hypotheses, critical tests, quantitative validation, this applies broadly across all of science. In conclusion, the photoelectric effect demonstrated threshold behavior that classical wave theory could not explain. Through systematic experimentation and Einstein's quantum hypothesis, we discovered that light consists of discrete photons with energy h nu. This revolutionized physics and launched quantum mechanics.